Hi everybody, welcome to the lightning talk of our paper which is accepted and published in IEEE Computer Architecture Letters. I am Seyed Morteza Nabavinejad and I will give this short talk. Various systems are proposed for DNN inference based on different hardware platforms. The deployment of applications on these platforms, however, has the similar structure, allocating a specific amount of hardware resources and adjusting the DNN side control knobs such as batch size. Finding and selecting the right configuration, for example, number of cores, amount of memory, and batch size, is essential for improving performance and power efficiency of the system. You can see in the plots that when we keep other parameters fixed and only change one of them, number of cores or batch size, how the power and throughput change. Furthermore, combination of these control knobs create a huge state space or configuration space, where the relationship between the control knobs is very complex and hard to model. So, it is challenging to find the proper configuration for various objectives and constraints. One solution for this problem is to test all the possible configurations to find the optimal one. While this approach can guarantee the optimality of solution, it is very expensive and imposes significant overhead that might not be feasible for a large subset of jobs. One alternative is to test a subset of all the configurations, which we call sample points, and find the solution based on them. The overhead of this approach is remarkably less than exhaustive search, and hence can be applied to a wider range of jobs. However, in this approach, finding the optimal solution is not guaranteed, and we may end up with a near optimal solution. Moreover, the way that the sample points are selected directly affects the quality of solution. So, we need a mechanism that is able to select the sample points wisely. To this end, we have designed and implemented BayesTuner. It leverages the Bayesian optimization to select the sample points and find the solution in a reasonable time. Bayesian optimization uses a prior function such as Gaussian process to estimate the target functions, for example, power and throughput, based on the control knobs. As more sample points are tested, the accuracy of estimated functions increases. The sample points are selected sequentially. One is tested and based on the result, the next one is selected. For selecting the sample points, Bayesian optimization uses an acquisition function. Based on the current estimated functions and the sample points tested until now and their outputs, acquisition function selects the next sample point. This process continues until reaching the maximum predefined number of sample points. More explanation on Bayesian optimization, our BayesTuner approach, and the results obtained by conducting experiments on a real-world setup can be found in the paper. Thank you for your attention.